Hello all, it's the end of chapter 6 and we are going to finish our last note today. So it should be Friday today. I'm going to leave you with some last questions. I will post the review because I'm going to remind you Monday is a review period and a live class. Tuesday will be our test for chapter 6, and then chapter 7 we get to basically put our calculators away, all these formulas and equations and calculations basically away, and we're going to start looking at a different type of chemistry. All right, so ultimately, I said to you before, this is kind of the bread and butter of chemistry, is looking at how much of this we need to add to how much of that, and how much product are we going to get, or if I need how much product, this much product, how many grams of each reactant do I need? Again, this is really what chemistry is largely about, but we need to go beyond that now to look at some more of the theory. So before I finish this last part of chapter 6, maybe I should do one sample problem from the homework from yesterday. Okay, I'm going to do one question from the homework, and then I'm going to move on to 6.7. Okay, so the question I'm going to do, I think it's question 7 from page 225. So that was the homework from yesterday, which was questions 4 to 10. Was it 4 to 10? Or was it 7 to 10? Might have been 7 to 10. Okay, so question 7 says, iron ore hematite is Fe2O3. It's an important source of iron on Earth. The iron extracted from hematite using carbon monoxide. So the reaction is this. Fe2O3 is hematite. Okay, it's a mineral. It's a naturally occurring mineral. Find it all over the world. If I go to areas that are rich in iron on the planet, again, some areas are famous for having large amounts of this, that, or the other. So there are areas that have got maybe gold deposits, and maybe we have a gold rush to those areas. I'm from Sudbury in Ontario, and in Sudbury it's famous for its nickel and copper. So again, if you go to Sudbury Basin and you are digging in your garden or doing anything, hiking around in the woods, the rock contains nickel. So hematite is another one. It's Fe2O3, and it's a mineral that contains iron. Now, I want to get the iron out of this rock, so I'm going to react it with carbon monoxide. And when I do, I'm going to get free iron, and I'm going to get carbon dioxide. Now, I should just fix this up here for a minute. It was 3 carbon monoxides. Okay, so there's the chemical reaction that we're going to undergo. So this is what I'm getting out of the earth. This is what I want here in Hamilton to make steel. Stelco, Dofasco, National Steel Car, all these steel companies. All right, this is what comes out of the planet. This is what I need to make steel. So the question is, how do I make steel? I'm going to react this that came out of the planet with carbon monoxide, and I'm going to get my iron. So question says, if 1 mole of hematite, okay, so we're getting number of moles here, reacts with 6 moles and equals 6 moles, which one is limiting, and how many moles of iron are going to be produced? Oh, this is a really easy question. Okay, so limiting one. So again, when you're trying to find limiting, so we already know the number of moles. We already know N. We're not having to calculate the number of moles. We're given the number of moles. Now remember, to find the limiting one, we take the number of moles and divide it by the coefficient in the balanced equation here. For iron 3 oxide, hematite, it's 1. And for the carbon monoxide, I'm going to take my 6 moles that were given, and I'm going to divide it by the number in the balanced equation here, which is 3. So when I do my math, I get 1 on this side, and 6 divided by 3 is 2. The lower one is the one that I'm interested in. That's this one. This is the one that's limiting. The other one is 2, so it's in excess. Means there's too much. So I don't need this anymore. I ignore the excess one. And now I'm going to do my mole ratios. So my mole ratios say the number of moles of my unknown, which is iron, divided by my number of moles of known, which is Fe2O3, just move this up a little bit, are equal to the number of moles of iron in the balanced equation divided by the number of moles of Fe2O3 in the equation. So, I know my number of moles of Fe2O3 in the question. It is 1. We were told that in the question. So, let's just move this up a little bit higher. So, number of moles of iron is unknown, right? That's what I'm trying to solve right now. Is how many moles of iron am I going to get from this reaction? So, let's go back up. So my number of moles of Fe2O3 was given in the question as 1. If I look at my balanced equation, I'm looking at iron and Fe2O3 here. So let's go to my balanced chemical equation. I know that there are 2 irons and 1 Fe2O3. 2 irons and 1 Fe2O3. So my number of moles of iron is 2, and my number of moles of Fe2O3 in the balanced equation is 1. So now if I do the math to solve for the number of moles of iron here, let's take the 1 up, multiply it by 2. So 1 times 2 is 2, divided by 1 is still 2. So my number of moles of iron is 2 moles. And that's the actual answer. That's the whole thing. Okay, so that's a lot simpler than the ones that we were doing before. Maybe I should have picked one from later in the chapter, but maybe tomorrow when we come to class, I will, to our live class on Monday, I will do one more question that's a little more complicated. If you want to see one of the ones done from the end of the chapter, like perhaps question 26, let me know and I can do another one and I will post a solution for you, a full solution. Okay, so there's the end of 6.6. Now I want to go to 6.7. Now 6.7 is a really important one because if I told you that carbon reacts with oxygen to make carbon dioxide, or let's get rid of that. Let's do something a little bit easier. Let's say if I told you that sodium, 2 moles of sodium, react with a Cl2 chlorine gas to make 2 molecules of sodium chloride, which is salt. Okay? And I told you how many grams of sodium we have and how many grams of chlorine we have. And we did all the math. We calculated the number of moles here and the number of moles here. And we did our work. And we finally came up with, we used the N value from here over to here and calculated N, and then we used it to come up with a mass, and we found the mass of sodium chloride. And the answer is, I don't know, let's say 17 grams. Okay, so that's what's supposed to happen. I sent you home the night before the lab, and I said, I'm going to give you 20 grams of sodium and 20 grams of chlorine or whatever. I'm making some numbers up. Go home and calculate, do the question that's on the test, which is this question, and figure out how many grams of sodium chloride we're supposed to get. So you go home, you do the work, and you all come back with the same answer, and it's right, and it's 17 grams. I said, okay, here we go. Now, I'm going to give you so many grams of chlorine gas, which I couldn't because it's poisonous, but let's pretend I'm going to give you so many grams of chlorine gas and so many grams of sodium. I'm going to say, do the lab, and when you're done, collect your sodium chloride salt and weigh it, and then write up your lab to tell me how it went. So you do the lab, and lo and behold, one group gets 12.6 grams of sodium chloride, and you think, whoa, it's supposed to be 17. You say, you talk to the next group and say, how did you guys do? And they say, we got 11.1 grams. You talk to another group and they say, we got 13.8 grams when we did the lab. So everyone's looking at each other thinking, what's going on here? Why are we not getting 17 grams? None of us got 17 grams. But Mr. Sinha gave us all 10 out of 10 for doing the calculation. He told us, yep, you're right, the answer should be 17 grams, but none of us are getting 17 grams. Okay, that's the reality of doing chemistry, right? So let's get rid of this. All my scribbling all over my note here. Okay, so what I want to look at is when we do a lab, okay, what we've been doing in all of sections 6.3, 4, 5, and 6 is calculating how much product we should be getting when we do a lab. If I tell you how many masses of reactant that you have, you should be able to calculate how much product you're supposed to get, right? So on my calculator, I can calculate the amount of product. I can do it with a pen and paper and a calculator, and I did some on the whiteboard today. I did some on the video that I did today. I did some on yesterday night's video, the night before that's video. I'm calculating the amount of product we're supposed to get. Okay. However, when we do the lab, we don't usually get the amount that we're expecting. You go, well, why not? That's what chemistry is about. You do the calculations, you figure out how many grams you're supposed to get, and you do the lab and you get it. Well, in reality, when we actually do the lab, we usually get less than what we were expecting. And well, why would we get less? If this is what the math tells us, and math never lies, how could we possibly get less? And the answer is there could be a number of different reasons why we could either lose some of our product, or, well, basically that's it, because we probably did create the amount that we wanted, but we weren't able to recover it all. Some of it got maybe washed away with our some of our reagents, some of it maybe got spilled, some of it went here, some of it went there, but in reality, most of the time we never get 100% of what we were expecting. So there's two amounts here. There's the amount that we were supposed to get in theory, right? That's what my calculator told me. Then there's the amount that I actually got when I did the lab, right? When I actually did the lab, how much did I really get? And it's usually less than what we expected to get. So I've got two amounts now. So let's say that lab that we were talking about a minute ago, and you were supposed to get 17.0 grams according to your calculator, according to Mr. Sinha, according to everyone else in class, but you got 11.1. Okay, so what are some of the reasons why this could have happened? Well, again, lots of different reasons. Okay, what can ultimately happen will be if I weighed out so many grams of the reactant out of the bottle, but the reactant wasn't 100% pure. If it was only 90% pure, then I really only added 90% of what I thought I was adding. And then when I'm done, I can only get 90% of the product. So I've lost 10% right there just because the reactant wasn't pure. It wasn't what I thought it was going to be. Okay. It's also possible that when I'm doing the lab, some of my chemicals may get lost. They get washed because when I'm washing my crystals, some may dissolve and go down the drain, right? All kinds of reasons. And again, if we were doing some labs, we'd see what some of the possible reasons are that we get less than what we're expecting to get. Sometimes, when I'm trying to make a chemical reaction happen, like we were just doing a minute ago, carbon plus oxygen makes carbon dioxide, sometimes we get something totally different. Right? The sodium plus chlorine, sodium plus chlorine gas makes sodium chloride. Maybe I get something different. Right? Maybe I get an this is impossible, but maybe I got an NaCl3 by mistake instead of getting NaCl. And the NaCl3 dissolves in water, so when I wash my NaCl, some of the NaCl3 disappears, and it didn't turn into, this didn't become AB, it became something else, right? And when I finally figure out how much AB I got less than I was expecting because some of it turned into something that I really didn't want in the first place. So that's a possibility too. Okay. Third possibility, and this is quite common and quite a problem for chemists, is chemical reactions can go backwards. Well, hang on, chemical reactions can't go backwards. If Na can react with Cl2 to make NaCl. What do you mean I can take NaCl and turn it back into Na and Cl2, make it go backwards? Well, it turns out that there's a lot of chemical reactions, almost all chemical reactions, have the ability to go in both directions. Now, you think, well, why don't when you make this first reaction happen, Na plus Cl2 makes NaCl, if it can go backwards, why doesn't all that NaCl turn back into Na plus Cl2? Well, sometimes that happens, right? And then what we end up getting, again, is less than what we were expecting to get. So what we need to do is calculate how good was our lab. What percent of what we were expecting to get did we get? We know percents really well because we've been doing percents on marks and on tests and on assignments and on everything we've been doing for the last 12 years of school, right? You've been getting percents. So now we need to do a percent again. And when I do a percent, we've got a calculation for something called the percent yield. This is the formula. It's our last formula for this section. Percent yield says, let's look at how much we got when we did the lab. Let's divide that number by the amount that we were expecting, our theoretical, our calculator value, and multiply it times 100. So the answer, so if I was doing a lab and I was expecting to get 10 grams of product, but when I did the lab, I only got 8 grams of product. My actual yield on top here is 8 grams. My theoretical yield, what I'm supposed to get, goes in the bottom here, 10 grams times 100, which tells me I got 80% of what I expected to get. That's my percent yield. Now, what that's telling me is maybe I didn't do too bad. If I got an 80 in a class, I might be pretty happy with that. If I'm a company and I've lost the other 20 that's not there, is what's been lost. Okay, and if I've got 80 but lost 20, that means if my product is what I've lost 20% of, then I've lost 20% of my product. I've lost 20% of my revenue has just gone down the drain or wherever it disappeared to. So we need to be thinking as we're doing our labs to make sure that we are going to lose the minimum amount so that we can maximize our profit, right? And again, that's how the world of work works. Okay, so I've got 2 samples here. Oh, there's 3 samples. I'm going to do the 2 bottom samples. I'm going to do this iron 3 oxide one, which is the one we were just talking about a minute ago, and then I'm going to do this second one down here. Okay, so I'll leave this top one, and you can try this one if you want to try this one, or maybe I can come back to this one in our next class on Monday. Because again, this is a pretty big question. So let's look at this sample here. Okay, it says when 1150 grams of iron 3 oxide react with excess carbon monoxide, we got 635 grams of iron, and the question is, calculate the percent yield. Okay, so let's go to our whiteboard here. Okay, and here's the same equation that we were working with, so let's just start again. So let's look at the sample. This is from section 6.7. Okay, and the sample says I'm going to take Fe2O3, which we were calling hematite, and react it with carbon monoxide. There's 3 of them, and I'm going to get 2 atoms of iron, or 2 moles of iron, and 3 moles of carbon dioxide gas. Okay, and the question is telling me that we are starting with 1150 grams, I believe it was, of iron 3 oxide with excess, again, so notice this is a really important word here, excess carbon monoxide. So let's go back to my question for a minute, and it says we get 635, so 1150 so my mass of iron oxide was 1150 grams. And it says the mass of iron was 635 grams. Now you think, well, hang on a minute. I thought we were trying to figure out how much iron we were supposed to get. Okay, well, the answer is we are. This is not how much iron we were supposed to get. This is how much we actually got. What I'm trying to do in this question is find my theoretical amount, my calculator amount. Okay, and when I find that amount, then I can use this number here to calculate how good my lab was. What was my percent yield? So I'm going to follow the same steps I did before. So let's get rid of this. And I've got a couple of important pieces to add to this question. Number one, we were told that there was excess carbon monoxide. Oh, so that means I know that this is limiting. Right? I don't have to do all the math for carbon monoxide to figure out which is limiting, because I know this is limiting. We're told right in the question there was excess carbon monoxide. So I'm going to go ahead and do the math the way we normally would. I've got Fe2O3 here. So Fe2 is 55.85 times 2. Fe2 plus 3 oxygens is 159.7. What I'm trying to find is how much iron am I supposed to get when I do this lab. And to do that, I'm going to follow the same steps we've been doing. I need to know the molar mass for iron. Right, the molar mass for iron is 55.85 grams per mole. Okay, so I'm going to do like I've been doing. I'm going to use my mass to find little n. I'm going to use my mole ratio to find little n here. Use my molar mass to find the mass of iron here. Right, and then I'm going to know how much iron I'm supposed to get when I do this lab. Excuse me. So, to find my number of moles on this side, I'm going to take the mass divided by the molar mass. Mass is 1,150 grams. It's a lot of iron. It's almost 2.5 pounds of iron. And I'm going to divide it by the molar mass, 159.70. And I'm getting a number of moles, which is 7.20 moles. Now, I already know this is limiting because they told me it's limiting. So I can go directly from there now to my mole ratio. So my mole ratio says I'm trying to calculate my number of moles over here so I can calculate my missing mass on this side over here. So to find that mass, I need to know the number of moles and molar mass. I know the molar mass from the periodic table, so I need little n. This is my unknown right now. So I'm going to find little n using my mole ratios. So I'm going to say the number of moles of iron, which is my unknown, divided by my number of moles of Fe2O3, which is my known over here, Fe2O3, and I know I have 7.2 moles, is equal to the number of moles of iron divided by the number of moles of Fe2O3 from the balanced equation from up here. Right? So remember, this side here is from the question. This side here is from the balanced chemical equation. So let's just scroll up here. I know that I have 2 irons and 1 Fe2O3. Two irons and 1 Fe2O3 in the balanced equation. I know that my number of moles of iron is unknown, and that my number of moles of Fe2O3, I can see it up there, is 7.20 moles. It's right here, the number of moles we just calculated a minute ago. So if I'm trying to find my number of moles of iron, it's going to be 7.2 times 2, which is 14.4, divided by 1. So I'm going to get 14.40 moles. Okay, now I know my number of moles, 14.40. I can put it in here. And now I can calculate my mass because I know little n and big M. Mass is equal to number of moles times molar mass. Number of moles is 14.40 times the molar mass of 55.85. And I'm getting 804 grams. Okay, so when we did this lab here and I did this experiment in the lab, in the chemistry lab, I put in 1150 grams of iron 3 oxide with more carbon monoxide than I need. I put in tons of carbon monoxide so I wouldn't run out. And that way this becomes limiting. And because this is limiting, I use this to calculate the amount of iron I'm supposed to get. And I did the lab, I'm supposed to get 804. Oh, but when I go back to the question, it says when we did this lab, we only got 635 grams of iron. So we were supposed to get a different amount. We ended up recovering 635 grams. So if I go back to my over here now, let's scroll this up, and now I want to figure out, the boss says, yeah, okay, so you got 804 grams. I say, yeah, I'm pretty happy with my 635 grams. He says, yeah, what was your percent yield? In other words, how good was it? Again, think about how good your test mark was as a percent. Right? If you got 38, you say, I got 38 on my test today. You say, yeah, well, that's okay. What was it out of? You say, it was 38 out of 40. That's pretty good. If it's 38 out of 80, that's not so good. Right? So I need to know as a percent, how good was this lab? So I'm going to actually calculate my percent yield. The yield is what I get. And my percent yield is the actual amount that I got in the lab divided by the theoretical amount, in other words, how much I thought I was supposed to get, times 100. Now, I know that my theoretical yield, what the calculator told me, was this number here. This is what I'm supposed to get when I do the lab. I did all the calculations just the way I'm going to do on the tests and get perfect on the question, and I got 804. That's how much I am supposed to get. However, when I actually did the lab, I only got 635 grams. That's my actual yield. So to calculate how good the lab was, my percent yield, I'm going to take my actual yield of 635 grams, divide it by what I was supposed to get, which was 804 grams, times 100, and I'm going to get 78.9%. .9%. So that means when I actually go into the working lab and get my lab coat on and my safety goggles and I do the lab, I recovered about 78.9% of what I thought I was going to get. Almost 80% of what I thought I was going to get. Again, that's maybe not so good because it means I've lost 20% somewhere. I don't know where that 20% went, but when I did the lab, I got 78.9% of what I expected to get. Okay, so that's what percent yield is. I don't know if this formula is on your periodic table. If it's not, you may want to add it to your periodic table. I think it probably is. I can kind of half look it up while I'm talking to you here. But I want to go back and I want to do the second sample problem. Oops. Okay, so the second sample problem here talks about the element arsenic on the periodic table. And it says when we collect arsenic, we collect it from the ore, again from rock. And the arsenic that's in the rock comes in this compound here, which has iron, sulfur, and arsenic all together chemically bound. And what's going to happen is I'm going to take that rock, FeSAS, contains arsenic, and I'm going to react it, probably heat it, and when I heat it, arsenic is going to separate itself from the FeS. Okay, so there's the ore, there's the rock that I'm going to start with. That's what an ore is. An ore is a rock. So let's FeSAS. It's going to decompose into FeS plus arsenic. Now, nice thing about this is it's already balanced. If I've read the question correctly, FeS AS gives me FeS plus arsenic. Okay, there was our last question that told us we were supposed to get 804 grams and we had a yield of 78.9%. Okay, let's continue on with this question. So it says we're going to start with 250 grams of rock and we got 95.3 grams of product. Right, now I'm not going to put my mass in here as whatever number of grams it was, because that's not how much I'm supposed to get. What's on my whiteboard in front of you right now is the calculation. Right? What the other part of that question is, right, this number here is not the calculation. This 95.3 is what I really got when I did the lab. Right? This is not what I'm expecting. This is what I'm actually getting. So I'm going to go back to the question that we were doing a moment ago, and I'm going to try and figure out how much am I supposed to get when I do this lab. So to calculate the mass over here, I need to know number of moles and molar mass. I can look up my molar mass from the periodic table for arsenic. It is, if I can find arsenic, 74.92 grams per mole. Grams per mole. And if I look at the molar mass of my ore, I'm going to have an iron, which is 55.85, plus sulfur, which is 32.07, plus the arsenic, which I know is 74.92, and I'm getting a molar mass of 162.84 grams per mole. Now, I can see, just like all the other questions, I have a missing mass here, I have a known mass over here, so I'm going to calculate little n, use my mole ratios to go to this side, calculate my mass on this side. So, number of moles, mass over molar mass, 250 grams divided by 162.84 grams per mole, and I'm getting a number of moles of 1.54 moles. Now, I can do my mole ratio, but I can kind of see that whenever 1 mole of FeSAS disappears, 1 mole of arsenic is made. So if 1.54 moles of FeSAS is used, I should get 1.54 moles of arsenic because it's a 1-to-1 ratio. When I multiply my number of moles times 1 over 1, I'm going to get the same number I had before. So I can use this number now and say, well, this is nice because I don't even have to do that mole ratio thing. I can just look at the fact that if I had 1.54 moles on this side, I've got to have 1.54 moles there. So now I can calculate my mass on this side as the number of moles times the molar mass. Right, and I'll end up with 115 grams. Okay, so that's what I'm expecting when I do this lab. I'm supposed to get 115 grams. Okay, so the question isn't, what are you supposed to get? The question was, this is how much you got. When we did the lab, we really only got 95.3 grams was collected. So the question is, what percent yield is it? So it tells me my theoretical mass is supposed to be 85.75 grams, which hopefully we got. Oh, sorry. 95.3. 115 grams. Sorry, brain's not working here. Nope, something's wrong with this number here. This isn't the right answer. So I get 115 grams. So now I want to calculate my percent yield. So to calculate my percent yield, it's my actual recovered amount divided by my calculator amount, the amount that we just did on this page here a moment ago, theoretical, times 100. Okay, so my actual yield was 93 grams. I think it was 93.5 grams actually. I should be writing this down. 95.3 grams is how much. 95.3 grams is the amount that I actually recovered. Divided by what I was expecting, which was 115 grams, times 100, and I can figure out my percent yield. So let's do my 82.8%. Okay, so when I did this lab, I recovered 82% of what I thought I was going to get when I did the lab. Okay, so that's what percent yield is. Okay, so I am going to finish there and leave you with the last 3 questions. Maybe I've made a mistake somewhere in my calculations because something doesn't look right. Okay, I'm going to leave you with the 3 questions on page 230, which aren't even here. Practice questions on 228. Okay, so these are 2 questions on page 228 here. Questions 14 and 15. There is question 5 on page 233. And then you can start the chapter 6 review, and those are the questions there. And if I will spend some time over the next couple of days and post the answers for the review in our answer package that goes with our textbook. Okay, so I will leave it at that for today. And good luck with the percent yield calculations. Take your time with them. Give yourself lots of room because, again, they're big questions. And you want to make sure as you're working through this that you've got space, that your stuff doesn't get crammed together like it does on my little screen here. Give yourself lots of working room and try and finish up those questions. If you have any questions, please reach out. Put the questions in the discussion forum on the hub or just email them to me directly. If you are posting them, send me a remind so I know they're there and I will go looking for it and I will solve it right away if I can or within a short period of time. Okay, so good luck with all the work. Good luck with the review. I will see you on Monday, those of you who are able to make it. I will hopefully try to remember to record it. And again, reach out if you're having difficulties. And just be ready that after we're done this next 5 days or so, by next Wednesday, we'll be ready to move on to much less of a calculator-based chemistry. Almost none, actually. All of Unit 2, you will not use